condition that is to stop these recursive calls, right? Okay, now we learned that recursion, it's a powerful problem solving strategy where a function calls itself. And to avoid the infinite loops and stack overflow, the function must include a base case that stops the recursive calls. Okay. So here is a couple of examples. Basically, the first one is looking at it conditions when to break, right? If x equals 0, then return, right? So that's one condition. Then this is second one is also another example to see recursion 1 and 2, right? So these are just some examples, but we're gonna look into these in detail in a minute, okay? So there are different ways, right? So first we already know is the loops. Loops are, as we know, is an iterative structures that repeat a block of a code multiple times, right? So they are commonly used for the tasks where specific numbers of repetitions are required, right? So for example, if we want to print numbers, right? Or like as you see on the screen, and the first one is a function recursion one. So for I, and then we have the loop I equal to 10, I greater than 0, and I minus minus, right? So this loop starts with I at 10 and then decrements until I reaches 1, right? And then every time it is printing the value of I, right? So that is the first part. Then the second one is the function rect2 is that is also that it is incrementing. It's in the for loop. The loop starts with I at 1 and then it increments until it reaches 10 and it prints each value of I. Now, so that is one, but then we also have a recursion. Recursion is an alternative approach where the function calls itself to solve the problem, right? So now how would you modify this? Basically is that um, you can rewrite this but with a condition, if condition in between, right? So you may want to write, like, for example, I'm just telling you, right? So void rect1 of int I, then you put an condition that if I is greater than 0, then print I, and then rec1 I minus 1, right? So now here there is we are calling this rec1 of 10, right? So then now when it starts to print, it basically is like, kind of removes one, decrements one, and then prints all the value, right? So normally, as we know, loops are more simpler. They are more intuitive for for a straightforward repetitive task, right? Because they use a single block of code to execute a repeated task until the condition is met. Whereas the recursion can be even more elegant for the problems that naturally fit in a recursive structure. Not all problems you can solve recursively, right? So you need to see whether you are able to solve it recursively or not, right? For example, if we are doing any tree traversals, or if we are doing famous math problem called Fibonacci sequence, right? So these kind of examples, they basically involve function calling itself with an updated parameters until the base condition is met, right? Now I just want to ask you guys, so what are the some of the advantages that advantages versus challenges that you know with the loops? What are some of the pros and cons of loops? Mm-hmm. Oh, just let me. Okay. Yeah. So loops generally use less memory because they don't involve function call overheads, right? And loops are pretty straightforward. They are easy to understand for repetitive tasks. But recursions on the other side can be more expressive and they can be more concise for problems that have more naturally recursive structures, right? So recursions can be less efficient, mainly due to its overhead of multiple function calls, especially if it is not optimized by the tail recursion, right? But we're going to look at that. I'm just giving you a heads up here, right? So both loops and recursions, they can achieve the same results, but the choice between them, it primarily depends on the specific problem that you are trying to solve, right? Okay. So here is the example that I was telling you earlier. So this was the one with the loops in order to decrement I, but here we write a if condition with a, like, with a base, right? And then you decrement. So here the example that you see is basically to show you how recursion works through a simple function, right? So the function here is printing the value of x and then it is calling itself with x minus 1, right? So reducing the value of x by each time, right? So here the main function calls, like, let's say in this case is a rec1 of 10, right? And then in the each call to rec1, it prints the current value of the x and then it calls the rec1 with x minus 1, right? Yeah, so those are just examples. So for example, all these lines are basically what it is doing is that we are calling, like, no, rec1 of 10. So it should print 10 and then it should also call rec1 of 9, right? When rec1 of 9 is called, then it will print 9 and then it calls rec1 of 8, right? So on and so forth till we get into the last part, that is the it's a rec1 of 0. Now, when it comes to rec1 of 0, the function checks if x is greater than 0. Since x is 0, then the function returns immediately without making any other recursive calls, right? Yeah. So now you may ask, like, why 0 is not in the output. So the function does not print the value when the x is 0 because the base case, if x is greater than 0, it prevents further recursive calls and returns before printing 0, right? So the recursion here or the output, as you can see, is like, it starts with 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, right? So the recursion here is involving a function calling itself with updated parameters until a base condition is met, right? So here the base condition, we can think of it as, like, x greater than 0. When x becomes 0, right, so the function stops making recursive calls, and that is why we don't see that in the output too, right? So the printed numbers are in the decreasing order from 10 to 1 as the function is printing the value before it is making the recursive call with x minus 1. Okay. So here is another example where the function rec2 uses a recursion to perform an operation after a recursive call, right? So there is a subtle difference between both of them, right? So first, what are we doing here? Is we are calling, right? So the main function calls rec2 of 10. Then at each call at rec2, first makes another recursive call x minus 1 before it is printing the value of x, right? So this is, like, slightly different than what we saw first. In the previous one, it was just printing first and then making the next call. Here it is making another recursive call before it is actually printing the value of x, right? So when you look at an example like this, can you tell me what kind of a data structure is used here? What is the data structure used here? Good. Yes. So now in this case, when the rec2 of 10 is pushing the value because it's a stack, right? So it and then pushes 10 onto the stack and then 9 onto the stack, 8 onto the stack, so on and so forth, right? So when it comes to again rect2 of 0, it hits the base case, that is x greater than 0 is false, right? So it returns immediately without pushing anything onto the stack. Now the function now starts also with returning rect2 of 0 up to rect2 of 10. How does it do? Each time popping and executing the deferred printf statement in a reverse order of the calls, right? So it is basically also popping at the same time. Even in this case also, the function does not print the value of x when x is 0, because the base case is x greater than 0. It is preventing that printf statement from being pushed onto the stack when x equal to 0. So that's why it is popping and then popping the elements in the order, right? So that is why you see that output of the function is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whereas supposed to the previous one, it's reverse, right? So the recursion is basically, it is deferring the operations to be executed after all the recursive calls have returned, right? So in this example, the printf statements are pushed onto the stack during the recursive calls and are executed in a reverse order as the function is unwinding, right? And we know that the base case x is greater than 0 is to make sure that the 0 is not printed, right? So the function starts printing from 1 once it begins returning from the base case. Okay. Then now let us look at one more example, that is the power using recursion. So to calculate the power of number using recursion, we can define a function that multiplies the base number by itself or exponent times, right? So how do we do it? As you can see here on the code, here we have the base case and also a reverse case. So when we look at such kind of an example, what do you think is the base case? What do you think is a base case? Just give it a guess and then I'll explain. Because we need to have a base case. No. So that base is different. Ariana, I don't know if you're getting confused with the base that we see in the exponents versus the base case that I'm talking. So when I say base case and a recursive case, these are the common terminology that is used in recursion. But in this particular example, you see power and a base, those are very much specific to this example of a power example, the base and an exponent, right? Yeah. First value. Yeah, so here in this code that you see on the screen, whenever you look at such kind of examples, whatever is the first one that you're seeing, let's say here while exponent not equal to 0, or even let's say if exponent equal to 0, right? Whenever we see something like that, your base case is that any number that is raised to the power of 0 is 1, right? And then your recursive case can it can go further on, right? So when this base case, let's say when the exponent is 0 and the function is returning 1, this is because any number that is raised to the power of 0 is always 1, right? Now we can do the recursive cases as however we want. So the function calls it, in the recursive cases, we know that the function is basically calling itself with an exponent decremented by 1. And then it multiplies the base by the result of the recursive call, right? So and then this will continue until the exponent reaches 0, at which point the base case returns 1 and the multiplication chain starts it stops, it starts to unwind, right? Yeah, so this recursive approach is to calculate the power that involves defining a base case where any number raised to the power of 0 and it returns 1. And for other cases, the function calls itself with the exponent decremented by 1 and it multiplies the base with the result of this recursive call until the base case is reached and the result is returned through the recursive call stack, right? Here is one more example of calculating the power using the recursion, right? right? So given a recursive function, we can calculate the power of a number. This is what we are doing here, right? Um, yeah. So first, what are we doing here? We are doing an initial call, that is like, power of 5 comma 2. That is, since exponent is not 0, the function returns 5 times power of 5 comma 2 minus 1. Here in this base, you see power base exponent minus 1, right? So which is 5 times power 5 minus 1. So that's the, and then you have, that's the then you the initial call, and then you have your first recursive call. First recursive call is basically power of 5 comma 1, right? And here also the exponent is not 0, the function is going to return that it is 5 times power of 5 comma 1 minus 1, that is 5 times power of 5 comma 0, right? And then the second recursive call is basically is your base case, right? That is power of 5 comma 0. Since the exponent is 0 in this case, the function is returning 1, right? Now we can so when the power 5 comma 0 is returning 1, now we can also resolve the previous calls, like, power of 5 comma 1 is returning 5, and so on, and we finish that until we get the final result, right? So these are the kind of like terminology that you need to remember. The first is the initial call. Initial call is like where the function triggers the evaluation. Then next we have is a first call. First call is first recursion when it starts, first recursion call. Then we have our base case. In this case is a power 5 comma 0. Right, and then the other terminology that you would want to kind of get used to is unwinding. Unwinding is basically the results of the recursive calls are used to compute the final result as the recursion is unwinding, and then you get your final results, right? So here the base case is that if exponent is 0 and it returns 1, right? So this is because any number that is raised to the power of 0 is 1. Then next we have is a recursive itself, recursive case, where if the exponent is greater than 0 and it returns base times power of base comma exponent minus 1. That's what we have it on the code on the slide right here. So this basically is multiplies the base with the result of the power function called with one less exponent, right? So basically this recursive approach is breaking down the problem into smaller sub problems until the base case is reached, right? It then combines the result with the sub problems to get the final answer, right? Yes, so the recursion, like as I told you in the very first beginning, it is a powerful technique, especially in a programming, where the function calls itself to solve smaller instances of the same problem. So the general structure of the recursive function, it mainly involves two parts. One is like, breaking down the problem and solving the base case, right? So what does it mean by breaking down the problem? In recursion, you can take a complex problem and break it down into a smaller, more manageable subproblems, right? So one of the subproblems is a smaller version of the original problem. That should be the condition there. Then the second part is basically your base case, right? So the base case, it is the simplest form of the problem which can be solved directly without further recursion, right? It serves as a like kind of a stopping condition for the recursive calls, right? So base case always serves as a stopping condition for the recursive calls. Okay. So any questions, like, before we move on? Do you understand this concept of recursion? Here again, we see the example of power, right? So here also the base case is that if exponent is 0, then it returns 1. This directly is solving the simplest version of the problem. Then the second one is a recursive case. If the exponent is greater than 0, then it should return the power of base comma exponent minus 1, right? So it is basically also breaking down the problem by reducing the exponent by 1 and making that recursive call, right? So recursion, there are like, kind of general constructs for recursive functions. So recursion, as we know, is a common technique to basically where the function calls itself to solve the smaller instances of a problem. But there are like two typical constructs that are used to define this recursive function. Again, this depends on whether the function returns a value or not, right? So the first construct is the function that returns a value, right? So this construct is often used when the recursive function is returning a value, right? So the structure includes like, base case that directly returns the final result and a recursive case that makes the recursive call with a smaller subproblem. Right? So in the first set of like, the code snippet that you see there we are seeing that the base case is that when the terminating condition is met, the function returns the final value 1. Right? If the terminating condition is not met, then the function performs a recursive action and it returns the result, right? So that is the first construct, that is the function that returns the return values. Next, we have is a second construct, that is void recursive functions. Now, what is this void recursive functions? So this particular construct too is mainly used when the recursive function does not return a value, right? So here the function is performing actions and then makes recursive calls until the base case is reached, right? So here now, what should be the base case? The function does not explicitly include the base case action because it naturally stops making recursive calls when the condition n, let's say, a condition is not met, right? And if the terminating condition is not met, then the function performs an action and then makes the recursive call to a smaller subproblem. Then that becomes a recursive case, right? So I'm just like, revising what we saw here. So there are two types of constructs. One is the function that's returning values, and the second construct is the void recursive functions. So in the first construct, the base case is directly returns the final result. And the reverse case is where it makes a recursive call and returns the result of combining the current action with the recursive result. Then in the second construct is the base case is implicitly it stops recursion when the condition is not met. And it in a reverse case, it basically is performing an action and makes a recursive call. Right? So these constructs are like, kind of common patterns that you see, but not always like, to write the recursive functions, right? So basically choosing the right construct depends on whether the function really needs to return a value or just simply perform the action recursively, right? So depending on that, we make the decision. So here is one example where we are doing a sum of numbers, right? So let's look at that example now. So here we are doing a recursive solution for the sum of natural numbers. To solve the problem of finding the number of first n natural numbers using the recursion, first we need to break it down into a smaller subproblems, right? So how do we do that? First we need to define it. That's the first step. So we want to find the sum f of n, which is 1 plus 2 plus 3 so on till n, right? And then use an iterative logic, right? So how do you write that? Um, f of n equal to 1 plus 2 of 3 plus so on till n, right? But this function is not directly a subproblem of the same problem. So we need to kind of we need a recursive definition that uses the same structure. Now, how do you do that? We're going to step 2 is to transform the problem. So we need to rewrite the sum in a way that it makes it clear how to break it down recursively. All right. So how can we rewrite this? So we can define the whole thing as f of n equal to n plus f of n minus 1. Right? I mean, if you solve this, it's the sum of numbers. You can write it like that, right? F of n equal to n plus f of n minus 1, right? Then we need to identify the base case. So the base case for the recursion is the simplest version of the problem I told you earlier, right? So which can be solved directly without further recursion. So in this case, the base case is that f of 1 equal to 1, right? So this is because the sum of first natural number is just 1, right? Now we can write the recursive function according to that. So which is basically just giving you an example. If let's say int sum of int n, let's say if n equal to 1, then return 1. That is your base case already, right? Then you write else return n plus sum of n minus 1, right? So your base case is when n equal to 1, the function directly returns n equal to 1 because the sum of the first n natural numbers is 1. Then for recursive case, for n is greater than 1, then the function returns n plus sum of n minus 1, right? So basically this is reducing the problem to find the first sum of n minus 1 natural numbers and then adds to it, right? So this is just an overview of a problem. Yeah, and here we are seeing the same thing but using a construct one. All right. So how are we doing it? We know that the sum of first zero natural numbers f of 0 equal to 0, right? So therefore our base case in this case is n equal to 0. Now we need to define the recursive expression here. So we have also know that f of n equal to n plus n minus 1, which we just saw here, f of n equal to n plus f of n minus 1. So this means that we need to return an expression that adds n to the result of f of n minus 1, right? So here is a little code snippet that you can see. The first part is a terminating condition, that is if n equal to 0 then return 0, that is your base case. Then the next part after the else is your recursive case where it is returning n plus a triangle number n minus 1, right? Yeah. So then we can also look at one more example on this construct one. So there are some classic examples for this recursion. Like for example, we have Fibonacci series, factorials, binary search, and string reverse. So these are some of very classic problems that you see always, right? Classic examples. And in the lab, in this week's lab, so TA is going to go over all those examples. Okay. First, let's get these concepts straight. Okay. So now what is a factorial? Factorial, you may have remembered from your high school math that for a positive integers n, the factorial is normally represented with, excuse me, I sneezed. Sorry. Um, Yeah, so what I was saying, the factorial, right? So for a positive integer n, the factorial is normally represented as n with an exclamation symbol right next to it, right? It is the product of all positive integers up to the n. And how do you write that? N factorial equal to 1 times, 2 times, 3 times, 4 times, 5 times, so on till n, right? Here you have the example of 4 factorial, right? 4 factorial is 3 times, 4 times, 3 times, 2 times 1, that's 24. Then in generally, we can say n factorial is n times, n minus 1 times, n minus 2 times, so on till 1, right? So that's in general. So in this case, our base case should be 0 factorial equal to 1, right? And then your recursive is basically the factorial function is naturally as you can see here, we can say confidently that it naturally falls under the structure of recursive, right? So this factorial function is naturally defined recursively because each factorial is related to the factorial of the next smaller integer. Okay. Now, what should be the stopping criteria here? So the recursion must stop at a base case to prevent infinite calls, right? So for a factorial, the base case is nothing but 0 factorial, right? So the 0 factorial equal to 1, right? Now to write a recursive function for calculating factorials, we need to know two things. One is our base case, that is already we know that 0 factorial is 1. Then we need to know the recursive case, that is n factorial equal to n times n minus 1 factorial, right? So we know both of them. Now with both of these, now we should be able to write our code, right? So the recursive function for a factorial works by mainly defining the base case, that is 0 factorial equal to 1, and then your recursive case, that is n factorial equal to n times n minus 1 factorial, right? So the function calls itself with a smaller problem size until it reaches the base case and then combines the result to compute the factorial of the original number, right? Now, this approach is mainly like taking advantage of naturally recursive structure of factorial definition. Okay. Yeah, so here is the example that I was exactly explaining just a minute ago. So the first part is we are declaring the factorial, and then the second part is where we are actually writing our base case as well as our recursive case. And for you to visualize the same thing that's happening here, how it is like, how the function is called. For example, here you have int fact definition, right? So that's the function and in its definition, but it's called in the main method, right? So whenever it is called in the main method, it is basically recursively giving us the output for each of the n values, right? So these two slides are mainly for you to understand from the visualization perspective. Okay. So then the other example we can see is Fibonacci numbers, right? So Fibonacci numbers are also defined recursively, right? So making them pretty straightforward to the code based on the mathematical definition, right? So how many of you already know what these Fibonacci numbers are? Okay. So Fibonacci numbers are like defined recursively. Yes, right. So recursively and making them as very like easy to understand, right? As you can see, the Fibonacci of f0 is 0, f1 is 1, fn is f of n minus 1 plus f of n minus 2 for all the integers, right? So it is 0 1 and 1 plus 1 is 2, and then 2 plus 3 is 5, and 5 and 8 I mean 3 plus 5 is 8, right? And so on and so forth, right? So yeah, so there are, I mean, this is just an example for you to show you. So even in this case, even in this case also the Fibonacci numbers, the code that you see, you have a base case if n is greater than or equal to 1, and then you have your recursive case, fib n minus 1 plus fib n minus 2. Yeah, each number adds its previous numbers, right? So this is just a one more visualization sake, but I'm pretty if these are high school math, right? So if you don't remember, that is okay, but this is the time to kind of revise your basics. But yeah, because this Fibonacci numbers and the factorial examples, these are some of the very, very fundamental examples that you will kind of come across in any programming language that you start learning, right? So these are the first ones whenever you talk about recursions. Okay, now let us look at one more example with the construct type 2. So in this example is where we are generating a tip chart, right? So we are generating this tip chart more recursively, right? So here we are writing a function that can generate a tip chart using a recursion. So this function will take in the lowest dollar value and also the highest dollar value along with some fixed tip rates and then print out the chart, right? So what should be a header? So header should be that the you can write it right. So you can say like the function prints out a chart with the appropriate tips for the meals ranging from first values to the last val numbers of dollars for every whole dollar amount. So both the parameters here are positive integers, right? So now coming to our recursive approach, how do we do that? The first, we need to determine the terminating condition. So what should be the terminating condition here? If your lowest dollar amount, that is your first value, is greater than your highest dollar amount, then the chart is empty and we are done, right? So your lowest dollar value, if it is greater than your highest dollar value, then we don't have to do anything. That's already determining the terminating condition, right? Then now that we know the terminating condition, the next step is to break down the task. So how do we break down? So first we need to see what part of the job we can perform, and then that is same as the main job, and then what is the recursion there, right? So first we calculate and print the tip of the current first value or the current lowest dollar amount, right? And then we call the function more recursively for the next dollar value, all right? For example, like I'm telling you, in the recursive case, the function calculates the tip of the current first value by multiplying it by the tip rate, right? Then it basically is printing the result in the form of for uh, for some dollar value, the tip is some x and y, right? So then it calls itself the first val plus one and moving one step closer to the terminating condition, right? Here, using this construct two, we defined a recursive function, right? The tip chart that basically is printing a tip chart for a range of dollar values. And then the function is recursively calculates and prints the tip for each dollar amount, right? That is like moving closer to the terminating conditions, first value that is greater than last value with each recursive calls, right? Now, when generating this tip chart using the recursion, the first value here we need to print is associated with the lowest dollar value. So this is because the chart must also start with the lowest value, right? Yeah, so here the first is that the first printout will be the tip of the lowest dollar value. After printing the tip of the current lowest dollar value, we are left with the task of printing the tip chart for the next range of dollar values from the current lowest value plus 1 to the highest dollar value. Yeah. So this is like, it's a recursive nature. So to generate a tip chart more recursively, we start by printing the tip for the lowest dollar value. Then we handle the sub problem of printing the tip chart for the next range of dollar values from current values plus 1 to the highest value, right? So this approach is like, it is leveraging this naturally recursive structure of the problem, right? So when it leverages the naturally recursive structure, what happens? It is making sure that each recursive call gets closer to the terminating condition. Yeah. Let's see here one more, like, with maybe with the code, and you can see easily, right? So here the code that you see is defining a recursive function tip chart that is basically printing the tip chart for a meal values that are ranging from first value to the last value using a predefined tip rate, right? Now here the tip rate is 0.15, right? It is already predefined, right? But you also see the precondition and the post conditions, right? So the precondition is both the parameters are integer with the first one being less than or equal to the second one, and the post condition is that a tip chart will be printed out with a row for each dollar amount ranging in between the values of two parameters, right? So here the base case is that your terminating condition, right? So what should be it if if first value, if not first value is greater than last value, right? It is basically checking if the first value is greater than the last value, and if it is, then function terminates without printing anything, and it is basically ending the recursion, right? So if the first value is less than or equal to the last value, then the function continues to the next steps, right? Then printing, then we print the tip also, right? So that's how you get this output, right? So where we are printing the meal dollar value and then also the tip, right? So basically the lines here, these lines are calculating and printing the tip of the current first value, and the tip amount is calculated by multiplying the first value by its tip rate, which is 0.15, right? Now, coming to the recursive, in the recursion, you can have like, tip chart, first value plus 1, comma, last value, right? So this calls basically the tip chart recursively. You see the tip chart already, right? So it calls recursively with a first value plus 1 and moving one step closer to the terminating condition, right? So the code snippet, like it's a very small one, but the code snippet is basically it's defining a recursive function that is generating a tip chart for the meal values between the first value and then your last value with a fixed tip rate 0.15. And the recursion is stopping when the first value is exceeding the last value, which means making sure that the chart is covering all the values in the specified range, right? So this is one of the problems that you're going to see in the lab as well. So it is to write a recursive function that prints a string in a reverse order, right? So now what you need to do to solve this, first you need to know what is a function prototype, right? So here the function prototype is void print reverse, which takes string array of character and then n of type integer, right? Then it determines the first character to print. That is the first character to print in a reverse order. So when you want to print in a reverse order, what should it be? It should be string of n minus 1, right? So now you're changing the index n minus 1. In the forward direction, it is always like, 0, 1, 2, 3. In a reverse direction, it is n minus 1, n minus 2, n minus 3, and so on. That's the reverse order, right? Indexing order. Then next we determine the breaking condition, right? So the recursion should stop when the length n is 0, right? So this means that all the characters it's been printed. The next we have is actually having a recursive call itself, right? So that is after printing the current character, we make a recursive call with n minus 1 to print the next character in the reverse order, right? So these are like, examples, and also you will, I mean, TA will go over the code in detail, right? And then here you have the solution also, like, right there using construct 1 and construct 2. Um, Here is one more example for you to practice. All the solutions are right here for you in the same set of slides. So here is that we are writing a recursive function that takes in two non-negative integer parameters and then returns their product basically. Right? Like for example, if you have parameters like 6 and 4, their product is 24, right? So you need to make that as a like kind of a generalized approach to solve that. So here you can use something called a recursive function, that is recursive multiply, that basically is calculating the product of two non-negative integers without using the multiplication operator by repeatedly adding one of the integers to the result of the smaller subproblem, right? So this method is using recursion to simulate the process of multiplication as a repeated addition, right? So you will see the solution here. But yeah, at any case, like, if you have any problems, come see me or TAs during the office hours. We are here to help you. Some more problems on this. Now, let us look at one more example. So, I mean, till this point, it is all recursion. So you have like all these examples and then their solutions also. So, oh, wait, hold on. Where is this? Okay, here. Yeah. Now, how would you apply a recursion to convert and print a decimal number into its binary equivalent? Right? So remember, the process is mainly involving repeatedly dividing the number by 2 and then noting the remainders. Right? That much we know about the division, right? So the remainder should be printed in a reverse order from bottom to top, right? So next set of slides are like, basically from the number system, right? So basically they serve as a reference for the steps to what we are talking about. Here in this case is we are showing how to transform from a base 10 to another base, like for example, base 2. In the exponent example, we already know what exponent and what base is, right? But base can always change. So that is what we are looking at, right? So transforming from base 10 to another base, like for example, is a base 2, but it basically is involving also employing the division remainder technique, right? So what is a division remainder technique? Like for example, for converting 117 base 10 to its base 2 would it follows like all these steps. So what are this? So 117 divided by 2, it leaves you 58 and the remainder is 1, right? And then 58 divided by 2 leaves you 29 with remainder 0. 29 divided by 2 is 14 with remainder 1. 14 divided by 2 is 7 with remainder 0, and 7 divided by 2 is 3 with remainder 1. 3 divided by 2 is 1 with remainder 1, and 1 divided by 2 is 0 with remainder 1, right? Now when we are reading the remainders from, we should always do it from bottom to top, right? Because now we know that we want to convert it into base 2, right? So the binary representation of this digit, like 117 in base 10, is basically 1 1 um 110101, right? Here, so here we are doing the same thing but programmatically. So here we are writing a function that is dec to bin, that is decimal to binary, right? Converting a decimal number into a binary representation more recursively. How are we doing? Here we have if n is less than 2 and then we print that value. Else we recursively call this function that is divided by function with n that is divided by 2, and then print the remainder of n that is divided by 2, right? So if the n, what should be the output? If the input n is less than 2, it means it is either 0 or 1, right? So we print it. Otherwise we recursively call this dict to bin by with n by 2, which effectively is dividing n by 2 and keeps calling it until n becomes smaller than 2, right? Now, while returning from this recursion, we can also print the remainder of n divided by 2, which gives us the binary representation digit by digit, right? Like for example, I don't know how much you remember about these bits, but normally when we read it, we read it from least significant bit LSB to the most significant bit, that is MSB, LSB to MSB, right? Again, this is also like, high school math, or even like, even before that. Okay, now coming to one of the other classic problems that you see, that is the Tower of Hanoi, right? So that in the Tower of Hanoi, or even you see like, kids playing it, right? So my son, he loves it. He always plays with that. Yeah, so the objective here is to move all the disks from the leftmost tower to the rightmost tower. So here our leftmost tower is our source tower and our rightmost tower is our destination tower. Now, how can we do the transition? We should leverage there is one more tower, that is the middle tower, or this middle tower is called an auxiliary tower or an intermediate tower, right? So when we move it, we also have to maintain the rule that no larger disk may be placed on top of the smaller one, right? So the condition is that we cannot place a larger disk on top of the smaller disk. And you need to move from your source tower to your destination tower through an intermediate tower, right? So this is literally like, as you can. Now, from this example, can you guess what would be the base case? Just give it a try. What would be a base case in this example? First of all, do you understand the problem? We have a source tower and we have a destination tower. Now we need to move objects or the rings from the source tower to a destination tower through an intermediate tower or an auxiliary tower. But the condition is that you cannot place a bigger disk on top of smaller disk. Mm. So here the base case is that if there is only one disk, right? So that is something that you need to see. So whenever there is only one disk, that becomes your base case, right? And then simply move it from the source tower to the destination tower, right? So that is your base case. Otherwise, we can use the recursive case. Now, what are my recursive cases? Recursive cases is moving n minus 1 disks from the source tower to the auxiliary tower using the destination tower as an intermediate, right? So that's one part. And then moving the largest disk from the source tower to the destination tower because we don't want this largest disk to be on top of the smallest disk, right? Then we move n minus disks from auxiliary tower to the destination tower using the source tower as an intermediate. Right, so I'm just repeating. So the base case is if there is only one disk, right? If there is only one disk, then we simply move it from source to destination, right? Otherwise, we do a recursion. Now, the recursive case is that we move n minus 1 disks from source to auxiliary using the destination as an intermediate, right? Then uh, we can also move the largest disk from source to the destination because you don't want the largest to be on top of the smallest, right? And then we move n minus 1 disks from the auxiliary to the destination, again using source as intermediate, right? So this is basically a recursive algorithm. It is this is to make sure that the disks are moved from one tower to another while they're also kind of maintaining the rules of the Tower of Hanoi problem. All right. So um, just some more kind of concise breakdown of the steps that are involved in solving this Tower of Hanoi problem, right? Iteratively or recursively. So for any number of disks, so the pattern is the same. So we shift n minus 1 disks from source to auxiliary, then shift the largest disk from source to the destination, and then shift n minus 1 disks from auxiliary to the destination, right? So this recursive pattern, again, like as I mentioned earlier, it is to make sure that the disks are moved correctly from one rod to another, when it is also maintaining the rules of Tower of Hanoi problem, right? So this is if you think of it, it is one of the most simplest but elegant algorithm with a more clear and structured approach. So, at home, try to practice this with these examples that you see here, right? So then it becomes very easy for you. Okay. So these are again for the illustration's sake. right? So here you see that um, I mean, again, so this output that you see here, it is basically is outlining a pattern for solving the Tower of Hanoi problem, right? So which basically is involving moving n minus disk from source rod to an auxiliary rod, and then moving the largest disk from source uh, to destination, and finally moving n minus 1. So here the shift n minus 1 disks, that is two disks from rod A to rod B, and then moving the largest disk, that is disk 3, from rod A to rod C, and then shifting also n minus 1 disks, that is again two disks from rod B to rod C, right? So this process is again like, making sure that all the disks are moved from rod A to rod C, and it is following the rules of the Tower of Hanoi problem. Right now, coming to its implementation, yeah, so it recursively moves the disk from one rod to another, and it is following the rules of Tower of Hanoi problem, right? So here the function Tower of Hanoi takes mainly four arguments, right? So that is the number of disks, n is the number of disks, and from rod, that is the source rod, and two rod is basically the destination rod, and then your aux rod is basically your auxiliary rod, right, or auxiliary tower. So now if there is only one disk, that is any one. Oh, okay. If there is only one disk, that is n equal to 1, it simply prints the movement of disk from source rod to a destination rod, right? Otherwise, what does it do? It recursively calls itself to move the n minus 1 disks from source rod to an auxiliary rod, and then it prints the movement of the nth disk from the source rod to the destination rod. And then finally, or recursively calls itself to move the n minus 1 disks from the auxiliary rod to the destination rod, right? So in the main function, you can set n equal to, like, the number of disks. In this case is we are setting n equal to 4, right? And then we call the Tower of Hanoi with the source rod A, destination C, and auxiliaries B, right? So now when we use this code, so it should correctly print the sequence of moves that are needed to solve this Tower of Hanoi problem for the 4 disks, right? Yeah. So when we run this code, and we'll see, like, the output, which is showing the movement of each disk from one rod to another, and like, also while following the rules of the problem, right? So this should be your output should look like. So the number of moves required to solve this is, like, for n disks is 2 to the power of n minus 1, and the number of function calls made to this recursive is also like 2 to the power of n minus 1. Since, like, there are 4 disks in this case, so replace n with 4, right? So now your total number of moves that are required is 2 to the power of 4 minus 1, that is 15, and your total function calls are also 2 to the power of n minus 1, that is 2 to the power of 4 minus 1, that is 15, right? So here this relationship, it is holding true for any number of disks, and it is also the fundamental characteristic of our Tower of Hanoi problem, right? Yeah, so this is one more illustration to show, like, how the recursion happens in this particular example. Um, then let's look at one more example, that is your fast exponent. Okay, so here we are using the laws of exponents, so we can optimize the recursive power function significantly by mainly reducing the number of multiplications that are required. So how do we do that? So here we can think of it as an optimization, right? So you have your int power, int base, and of arguments int base and int exponent, and if exponent equal to 0, return 1. If exponent percentile 2 is 0, then, or it's not, and it will give you result as shown here on the code, like base comma exponent minus 1. right? So here the exponent, we can also add something like even odd conditioning too, right? So here we can add even odd conditioning. So if the exponent is even, then we can divide it by 2 and recursively compute the result for half the exponent. Then we square the result to obtain the final result. So if the exponent is odd, then we subtract 1 from it and make it even. And then we calculate the result for reduced exponent that is divided by 2. Then we multiply the base one more time in order to account for that odd factor, right? So these are kind of examples that you can play around with, like, but you need to come up with an optimized approach, right? So this optimized approach is dramatically is also reducing the number of multiplications that are required, especially when you have larger exponents, right? So which is what is making it much more useful and efficient when you have naive recursive approaches, right? So here is one more example to handle the case when n is not even. Okay, right? So we can modify the algorithm and consider the both even and odd exponents, right? So how can we do that? So we can see if we can recursively compute the result for half of the exponent. So what does it mean? If the exponent is even, then we simply square the result. If the exponent is odd, then we multiply the base. Here you can see multiply the base one more with the squaring the result, right? So this is just the little modification to handle that case, right? So this modification is again to make sure that the algorithm is working correctly for both even and also odd exponents. And also additionally, like, if you want, the algorithm can still have time complexity, but we haven't covered the time complexity yet at this point. Like as I mentioned in some of the previous lectures, we're going to talk about the time analysis maybe in next 3 or 4 weeks, right? So then if you, when once you start learning that, then whenever you're solving such kind of algorithms, you always want to also include the time complexity of these, right? Of, for example, in this case is O of log n, because mainly because we are kind of dividing or halving of the each exponent at each recursive step, right? So here is one more implementation. So the power B function is another implementation to the recursive exponentiation algorithm, right? So it works similar to what we discussed previously, the optimized version, right? So these two optimized versions, right? So here, if the exponent is 0, then the function is returning 1. If the exponent is 1, then the function is returning the base. If the exponent is even, then the function recursively is calculating the base cap exponential by 2, and then it is squaring the result. If the exponent is again odd, then the function is recursively calculating base to the power of exponent by 2, squares the results, and then multiplies again with the base, right? You see the difference between when the exponent is even versus the odd, right? So in the odd, it is again further multiplying with the base, right? These are some of the optimization methods. So there are multiple ways how you can find it, but that's only comes by practice. In a first go, if you don't get it, it's absolutely fine. I mean, even if in the first 10 times, if it doesn't get it, that's also absolutely fine. It only like comes by more practice. The more you write the code, the more you program it, then you come up with more better thoughts, right? So programming is also being very creative, right? So again, coming back to our example, so this approach is again to make sure that the function works correctly for both even and also odd exponents, right? So in the main method, here we are printing the result of power b 2 comma 5, which basically is calculating to the power of 5, right? So the function will compute the result more recursively and then returns the value to be printed, right? So now when we run this code, what should happen? It should print the result of 2 to the power of 5, right? So which is 32. Yeah. Yeah, so here is one more example to find the result of f of 4 using a recursive function. Now coming to our recursive function, you can also like draw this. Here is a pictorial representation for you to follow, like like this one. So here also f of 4 can have like f of 2 and f of 0, and f of 2 can have f of 1 and f of 0, and so on and so forth. Right. So basically here, because we are kind of parting it by 2, right? So when f of 0, then it should return 0. When f is f of n is 1, right, f of 1, then it should return 1, right? So if f of 2, then it calls basically f of 1 and also f of 0, right? So that is sum of f of 1 plus f of 0, that is 1 plus 0 equal to 1, right? So that returns 1. So that's a recursive. These are some recursive examples. So now to generate all these permutations, right? So permutations are the ones that we're going to discuss in some time. So to generate all the permutations of a given list of items, here is we use the recursion. So the approach to generate these permutations is that first you need to know the recursive functions, right? And then the base case and also its recursive steps. So what should be a recursive function? We define a recursive function that takes the current permutation and the remaining items, and then they count as arguments, right? Next, we look at the base case. If there are no remaining items, then we print the current permutation, right? For each remaining item, we add or we append it to the current permutation, and then we recursively call the function with the updated permutation, and then the remaining items are excluding the current one, right? And then then last we initialize the empty permutation and call the recursive function with the initial permutation and the list of items, right? So here are just examples, but we're going to look at all those in a minute. Yes. So here, what are we doing? We are breaking down the permutation problem into more sub problems, and we can simplify the implementation, especially when you're using a recursion, right? So here, if the input string has only one character, then it returns the list that is containing just that character, right? For each character in the input string, we recursively also generate permutations of the remaining characters and then append the current character to each permutation, right? And then we combine the permutations in order to obtain the recursive step to form the final results, right? So in this example here, we see a permutation of a word CAT, right? So we can write a code to generate all the permutations of a string cat using a recursion, right? So which means it is following the approach of swapping the characters and then recursively generating the permutations for the remaining characters, right? So when we are looking at different permutations for each of the character, right? So each permutation is printed once it is generated, right? Now again we are breaking down the problem further, right? Um, so we can start applying this concept of breaking it into a smaller problems into to generate the permutation starting with the letter C first. Now to generate the permutations with letter C, we need to find all permutations of the remaining characters after C. What are the after characters after C? They are A and T, right? And then append C at the beginning of each permutation, right? So either you can do AT or TA, but you need to put C in the front, right? So similarly, you can basically here what you're doing is you're swapping the characters, right? So you can write a little code snippet where it can generate all the permutations of the string AT, and then it appends C to the beginning of each permutation, right? So which is basically giving us a resultant permutation starting with the C, right? So this is, if you can think of it, this approach is basically showing the recursive strategy of reducing the problem to a smaller sub-problems of the same form, right? So here also when generating these permutations of a string with a multiple characters, we also need to make a recursive calls for each possible starting letter, right? So here, like for example, we can take example of a science in this case, right? Or any word for that matter, you can do that, right? You can simply start writing simple if else conditions, and followed by that you want to have a for loop, right? Because you need to swap the characters, right? So that's the little logic to write this implementation. So once you write it, and it should generate all the permutations of the string, whatever the string that you took. In this case, is an example of a cat or a science. But if you want to have a better, or even more harder examples, you can try with that is by making the recursive calls for each possible starting letter, and it uses to generate a permutations function to iterate over each character of the input string and then generate the permutations starting with that character. Then each permutation is printed once it is generated. All right. So here we can also do like kind of a K, first K characters, right? So here for generating permutations where the first K character are fixed in the original position, let's say, then the terminating condition for the recursion would be when K is equal to the length of the string, right? So here is some just some more text to what I was telling you earlier. So here the recursive function is basically taking three arguments, that is the string uh, and then the k index, basically representing the position of the first character to fix, and then the index n to represent the last character index in the string. And when k reaches n, all the characters are fixed and the permutation is printed. Right? Now, to make sure that each character in a string becomes the first character at some point during the permutation generation process, we can actually also modify this recursive function to swap the characters at indices k and j. And how do you do that? You can do it before making the recursive calls, right? So this way, each character will have an opportunity to be the first position during the permutation generation, right? So here we are also using multiple loops, right? So I'm just repeating, no, to make sure that each character in a string also becomes the first character at some point during the permutation generation process, we can modify this recursive function to swap the characters at indices k and j before we make any recursive calls, right? So once you have something like this, then the loop is basically iterating over the characters starting from index k, and then it is swapping each character with the character at index k. And effectively, it is also making it the first character temporarily. Then it recursively also permutes the remaining characters starting from index k plus 1, right? So after recursive calls, it basically is also backtracks by swapping the characters back to its original position to explore other permutations. So what I mean by that, here we have, for example, is an exchange characters function, right? It is basically is swapping two characters within a given string, right? So the function is basically is taking three arguments, which is your string, your indices I and j, that is representing the positions of the characters to be swapped, right? It temporarily stores the character at index I and then it replaces it with a character at index j. Then replaces the character at index j with a stored character, and then effectively it swaps the two characters within a string, right? So here it is used as a recursive permute function to swap these characters during the permutation generation process. And how do we do that? Using the loop that we just discussed in the previous slide, right? So the function is basically is essential for correctly permuting the characters in the string. Now, so the process that we've been seeing is again to make sure that each character in the string has opportunity to be the first character in the permutation, right? So now let us look at the steps. Anyone remember what are the steps that we need to follow? Okay, so for in order to make sure that each character in the string has opportunity to be the first character in the permutation, so the process first involves is the first step is to loop over the characters. That is, the loop iterates over each character in a string starting from index k, right? Then the step two is to swap the characters. So within the loop, we use some kind of exchange characters function. It is called to swap the character at index k with each subsequent character j in the string. Then the step three is after swapping, the recursive permute function is recursively called with the updated string to generate permutations with the current character at the beginning. Right? Then the fourth one is again after the recursive call, the characters are swapped back to their original positions to explore the other permutations. That is called basically backtracking. Right? So this process is mainly to make sure that all the permutation with each characters are as the first characters as they are generated. Right? Oh, I see that we also have a exchange characters, right? So exchange characters, yeah. So that loop that you see on the very top in the top of the slide, along with this exchange character function and the recursive permute function, collectively is what generates all the permutations of a string with each character as a first character. So here is again the recursive permute function. It is basically a recursive implementation to generate all the permutations of a given string. Now let's see how it works. So we know that it's a base case, right? So if k is equal to the length of the string, all the characters in the strings are fixed, right? So the function basically prints the permutation that is stored in that string. Then the next step is to, that is our base case, we know that, right? So then our next step is to have a recursive step. That is, if k is less than the length of the string, then the function is iterating over each possible starting letter for the index k. It then swaps the character at index j with the character at index k, and then it is also effectively fixing the character at index k, right? So it is basically recursively calling itself with k plus 1 to permute the remaining characters, right? After the recursive call, it is again backtracking by swapping the characters back to their original positions, right? So that is the what's happening here in this part. And the function along with its exchange characters and is the one that's actually generating all the permutations of the string by systematically fixing each character and then recursively permuting the remaining characters. So here the base case is the recursive permute, right? So the function that is basically checking whether all characters in the string are fixed, which basically occurs when k is equal to the length of the string, right? So now when we are generating these permutations, when k reaches the length of the string, it means that all the characters in the string have been fixed in their positions and there are no more characters that are left to permute. So now what we should do at this point, we simply print out the resulting string because it represents one of the permutations of the original string, right? So this is why it is a base case that serves as a stopping condition for the recursion, right? So once all the characters are fixed, then we no longer need to make recursive calls to further permute the string and we can print out the permutation that we have generated, right? So it is very important to understand how this recursive permutation algorithm works, right? So when we saw that when base case meets, what if when the base case is not met? So when the base case is not met, that is when not all characters are fixed yet, then we need to continue permuting the string, right? So in this case, we enter a loop that iterates over each possible starting letter for index k, which is the first index for which we have a choice, right? Now inside this loop, we need to perform several tasks to generate the permutations. So how do you do that? First, we need to swap the characters, right? So we need to swap the character at index j with a character at index k, right? And it effectively fixes the character at index k more temporarily and allowing us to explore the permutations with the different characters at this position. Then we make a recursive call. So after swapping, we make a recursive call to recursive permute with k plus 1. And this recursive call permutes the remaining characters starting from next position after k. So after the recursive call, now we need to backtrack by swapping the characters back to their original position, right? This is also essential mainly to explore all the other permutations and then avoid duplicating permutations that have already been generated. Okay. Yeah. So in the loop, um, first what we're doing is we are iterating over all possible characters, right? So the loop iterates over each possible character that can go into the index k. Since k is representing the number of fixed positions, and we start iterating the index k to end of the string to consider all the remaining characters that are not fixed yet. Then what are we doing? We are placing character at the index k, right? So inside the loop, we place a character that is stored at index j in a location k, and it effectively is fixing the character at index k, and it allowing us to explore the permutations with the different characters at this position. And then after fixing the character at index k, we can make recursive calls to recursive permute with k plus 1, right? So this recursive call permutes the remaining characters starting from the next position after k, right? And then this process will continue until all the characters are fixed. Then after we receive the recursive call, we need to backtrack by putting the original character back in its place at index j. And it is essential, like as I said earlier, to explore all the permutations and to avoid any kind of duplicating permutations that are already generated, right? So basically this loop is effectively is generating the permutations by systematically fixing the characters at different positions and exploring all possible combinations of characters, and also making sure that each character has the opportunity to occupy each position in the permutation, right? Again, so we saw in the loop for each iteration we consider all possible characters that could be placed at index k by swapping the character at index j with the character at index k, and then it effectively is exploring all possible values that can occupy the position that's represented by k, which is allowing us to generate all the permutations in the string, right? I mean, these are like if you think of it, the last part, it may sound like it's a little bit of repetition, but that's just to give you more kind of understanding of what's exactly is happening, right? So in when we come back to our original input of cat cat, when k equal to 0, the loop iterates 3 times, right? So because the length of the string is 3, so during each iteration, the loop tries each character at index 0, since k equal to 0 represents the first position, right? So now what happens in the first iteration when j equal to 0, that is the character at index 0 is swapped with itself and effectively is also keeping it in its original position, right? So this does not change anything, but it's necessary to make sure that we consider all possible permutation. Then next we have is a second iteration, that is j equal to 1. Right, so the character at index equal to 1, which is a, is swapped with a character at index 0. Right, so this places a at the beginning of the string, and it is effectively fixing it at a first position. Right, then we recursively permute the remaining character starting from index 1. Right, next we have is a third iteration, j equal to 2. So similarly, the character at index 2, which is t, right? So we start with cat, right? So the last one is the t, is swapped with the character at index 0, right? So this places t at the beginning of the string and recursively permutes the remaining characters starting from index 1. Now, after each iteration, we backtrack by putting the original character back in its place at index j. Right? So, as I mentioned, so this is mainly to make sure that we explore all possible permutations of the string. Right? So, here it is. I mean, maybe when you practice, you'll get a clear understanding of how this loop is iterating over all possible or each possible character at index k, and it is generating permutations more accordingly. Right? Yeah. So just to recap a little bit, we iterate. So for the for loop iterates over each character that could potentially be placed at index k, and during each iteration, the character at index j is temporarily placed at index k using exchange characters function. Then this will also effectively fixes the character at index k and allows us to generate the permutations with that character at the beginning. Then after fixing the character at index k, the recursive permute function is recursively called with k plus 1 and to generate the permutations of the remaining characters starting from the next position after k. Right? After recursive call, we need to backtrack by putting the original character back in its place at index j. And it is to make sure that we explore all possible permutations of the string and avoid any kind of a duplicating permutations. Right? So basically, this process will continue until all the characters in the strings have been fixed at different positions and leading to the generation of all possible permutations. Right, so with that we are at the end of like recursions and the permutations. Now it's the time for any questions. If you have any questions, you can stay here, otherwise you are free to leave, and then I'll see you on Wednesday, but I'll be here till my office hours.
The recording has stopped.